All right, chemistry, we're beginning our third lesson in the kinetics unit, and it's on collisions. So collision theory states that the rate of a reaction will increase with 1, the increasing number of collisions of reactant molecules, 2, increasing the speed of reactant molecules. So fundamentally, chemical reactions happen when reactants, atoms and molecules, smash together and break apart, and then recombine into new substances called products. So the collisions are very important. If they don't happen, then you don't have a chemical reaction. So a collision must take place with enough energy to create a reaction. So the energy needed for the reaction to proceed is called the activation energy, and is the difference between the energy of the reactants and the highest point on the diagram. So these are called potential energy diagrams. You should recognize them and know how to interpret them. So on the left side of both of these diagrams, let's just take the diagram on the left. On the left side, you have two reactants, A and B, and they have a certain amount of energy in them already. Now, if you can put in enough energy called the activation energy, and that's known for different types of reactions, it's been tested, it's been shown what it is, then you get up to the top of that hill there, and it's actually called the energy hill. And the difference between the energy that A and B have naturally and what they need to break apart is called the activation energy, and that's abbreviated E sub A. So once they get up over that hill, they can then, it's like riding a bicycle, they can then ride the bicycle down to the bottom of the hill on the other side, and that's the products. And you see that in both of the diagrams. Now the difference between the two diagrams is the reaction, the diagram on the left is an exothermic reaction because the products C and D end up at a lower energy than A and B. That means they're going to give off energy, give off heat, enthalpy. On the right, the reactants are at a lower energy. You still need to put energy in to get them to break apart, and then they go down the hill on the right side. However, they end up at a higher energy. C and D end up at a higher energy. So again, the activation energy is the difference between the energy of the reactants before a reaction's taken place and the top of that hill. So there you see the potential energy diagrams again. So that's the activation energy. Now again, it's not from all the way at the bottom of the graph to the top of that hill. It's from where the reactants are, A and B, at the beginning. That's the activation energy. So this reaction is exothermic because the reaction ends at a lower energy than it began. This means energy left the reaction, and the reaction left releases energy, and that's negative delta H, negative enthalpy. This reaction is endothermic because the reaction ends at a higher energy than it began, so energy entered the reaction, and that's positive delta H. Activation energy is the minimum energy required to allow A and B to break apart. Once A and B have separated, they can go back to A and B. In other words, they could start up that hill and not quite make it to the top and fall back down to A and B. Or they can recombine to become product C and D. That means they'd have to get over the top of the hill. For both endothermic and exothermic reactions, energy must first be put into the reaction and must reach the activation energy. So no matter what the reaction is, you have to put energy into it to get it started. The broken molecules at the top that exist at the top of the diagram is called the activation complex. That's basically all the atoms and molecules broken into pieces before they get put back together again. As temperature increases, the rate constant increases. The higher the temperature, the more the rate constant increases. So we've talked about this, that the rate constant, which tells you how fast the reaction, it's one of the components to tell you how fast the reaction will take place, is dependent on temperature. But as you'll see by this curved graph, what it's saying is as the temperature gets higher and higher, the rate constant gets higher at a faster rate. In other words, it goes up more for a certain temperature change. The curves below are called a Maxwell-Boltzmann distribution. On the vertical axis is the number of particles, and on the horizontal axis is the molecular speed. The area under the curves is the same for all four curves. The red dashed line represents the activation energy, the minimum energy required for the reaction to take place. Higher temperatures means higher molecular speed. We talked about that when we talked about gas laws. The activation energy on the graph is 1,000 meters per second. None of the molecules under the turquoise have enough energy to react, because you can see the turquoise curve is entirely to the left of the activation energy. About half the molecules under the red curve have enough energy to react. So the higher the temperature, the faster the molecules, the harder they're going to hit each other, and the faster that the reaction will take place. So you should know how to interpret this graph right here, the Maxwell-Boltzmann distribution. The Arrhenius equation relates temperature, activation energy, and the rate constant. The Arrhenius equation is K, rate constant, equals A, E raised to the power of negative EA over RT. So let's go through what each of those is. So A is called the frequency factor, and it takes into account the orientation of the molecules. Orientation is important because molecules must strike each other in the proper direction. EA is the activation energy we just talked about. It's the amount of energy a molecule must have to react. Activation energy is the energy hill that molecules must climb in order to react. T is the temperature, and it has to be in Kelvin, not centigrade. And R is the gas constant that we used when we did gas laws. However, there are two different gas constants. The one we used with the gas laws mostly was the one you see in parentheses, 0.0821 liter atmospheres per mole Kelvin. But this one replaces liter atmospheres with joules, as in joules of energy, over moles Kelvin, so it's a different number. It's 8.314. You have to be sure to use that one when you do this equation. And E is 2.718, and that's Euler's number that we were introduced to earlier. The Arrhenius equation relates temperature, activation energy, and the frequency factor to the rate constant. So before we always said the rate constant was a function mainly of temperature. That's true, but it's also a function of these other things, the activation energy and the frequency factor. So there's the equation. So what is the relationship between the exponent negative E to the A, that's the activation energy over RT, and the rate constant? See what happens here. So when activation energy EA increases, then E raised to the negative EA over RT becomes smaller and K becomes smaller. In other words, if you raise the activation energy, that's going to mean it's harder for the molecules, the energy of the molecules, to get over that energy hill, and therefore the reaction will slow down. So raising activation energy makes it harder for the reaction to take place, and therefore the rate constant K goes down. When temperature increases, then that term E raised to the negative EA over RT becomes greater and K becomes greater. And we know that because as temperature goes up, the molecules go faster, they hit each other harder, and that increases the reaction. So we've said that K is largely a function of temperature. When frequency factor A increases, K becomes greater. In other words, frequency factor is how often and at what orientation the molecules are hitting each other. So the bigger that number is, the bigger the rate constant will be. So there's the Arrhenius equation. Now, there's a way we can do this. You don't need to understand the math, just learn the equation. And this involves taking logs of both sides and doing some math manipulation that you don't need to understand. If you're really interested, you can come see me after school and I can show you. But what you can get if you take logs of both sides, you end up with natural log of K on the left, and then remember the log and the E cancel each other out. So you end up with negative EA over R, times 1 over t plus the natural log of a. And again, you don't need to understand the math, but you may look at this and it may look familiar. It has y equals mx plus b form. So it turns that equation, the Arrhenius equation, into a straight line equation, where the independent variable, which is equivalent to x, is 1 over t. So you can change the temperature, and that will tell you how the natural log of k, the rate constant, will change. The slope of the line is negative EA over r. That's the m. And then the y-intercept is natural log of a. So again, we have a slope-intercept straight line equation. Again, you don't need to understand the math. Anytime I would ask you to use this equation, I would give it to you. We can use logs to create a straight line out of the data. That's what happened up above. And the slope is negative EA, activation energy, over R. Okay, so we can calculate K at a certain temperature if we know K at another temperature. And this produces this rather scary looking equation right there. So if we know the value of K at a certain temperature, let's say K1, and we know its value at T1, temperature 1, we can find the value of K at a second temperature, T2. So we know K1 and T1, that relationship. We want to know what K is going to be at temperature 2. So the variable, the unknown here, is going to be K2. So you have to be given all the other numbers. It's a little bit messy. I'll have you do one or two of these, and you'll see these as well on an answer video. We know that K changes with temperature. This equation gives us a way to take the known rate constant K for a particular known temperature and compute the rate constant at a different temperature. So the activation energy for the following first order reaction is 102 kilojoules per mole. The value of the rate constant K at this temperature is 1.35 times 10 to the minus 4, and that's at 35 degrees centigrade, which we have to convert to Kelvin. So that's 308 Kelvin. What is the value of K at 0 degrees? So we know the value of K at 308 degrees Kelvin, or 35 degrees centigrade. Now we want to find out what it is at 0 degrees centigrade. So common sense would tell you it's going to be less. Why? Because 0 degrees centigrade is less than 35 degrees centigrade. So it's going to be a lower temperature, and so the K is going to be less. So let's go ahead and do the calculation. So there's the formula. You're just going to plug in numbers for everything except K2. So the activation energy is measured in kilojoules per mole. This can be converted from kilojoules to joules because the gas constant below is measured in joules, so you have to make that conversion. So 102 kilojoules per mole is 102,000 joules per mole. Again, the gas constant we're using is the 8.31 joules over moles Kelvin. So let's go plug in. So there we have the variables that we were given on the previous slide. So the variables are K2 is what we're looking for, the second the second rate constant. T2 is the temperature at the new temperature, 0 degrees centigrade, 273 Kelvin. T1 is the original temperature, 35 degrees centigrade, 308 Kelvin. And the rate constant at that temperature is 1.35 times 10 to the negative fourth. The activation energy is 102,000 joules per mole. The R is 8.31 joules per mole Kelvin. So there's the formula. So we're going to plug in all those numbers, and it looks like this. It looks like a big mess. I'm not going to go through the units calculation. I'm just asking you to trust me here that you are going to end up with the units for a rate constant at the end. Okay, so here we go. So it's a little bit of math, and it's good practice for your math. So you inverse the natural log. Remember that process. So see the natural log over there on the left? You're going to make e raised to that exponent. So it looks like that. And on the right side, it's e raised to everything you see on the right side of the equal sign, and those numbers are going to end up to be negative 5.1. So now you just go ahead and do the e to the negative 5.1 on your calculator, and you know that e raised to the natural log of that term you see on the left side of the equal sign is just going to give you K2 over 1.35 times 10 to the minus fourth equals e raised to the negative 5.1, which is 0.00606. A little bit of algebra, and you get K2 equals 8.18 times 10 to the negative 7th, 1 over seconds. 1 over seconds means it's a first order reaction. So K equals 8.8 times 10 to the negative 7th is less than K1, 1.35 times 10 to the negative 4th, because the reaction runs slower at 0 degrees centigrade than 35 degrees centigrade. And that takes care of our lesson on collisions, and I'll give you a few problems to practice on this.